Modern theoretical physics is trapped. We're mapping a dynamic, curved universe using an empty, rigid, three-dimensional coordinate system. When scaled up, this model collapses. The Euclidean measurement fallacy stems from the assumption of flatness. Standard metrics apply a linear ruler to a manifold that possesses actual fluid viscosity and non-Euclidean curvature. This geometric friction produces the cracked egg artifact. When forced onto cosmic scales, these tiny baseline deviations compound exponentially. Legacy math relies on an inverse square law, ignoring the manifold's fluid scaling and causing a massive 120 order of magnitude discrepancy. Theoretical physics invented the concept of dark matter as a placeholder to account for this massive mathematical deficit. It functions as a fudge factor, designed to hide the discrepancy between our flat measurements and the curved pressure of the vacuum. Legacy models fail because they treat this mathematical variance as a noise floor to be smoothed over. If we want to understand the universe, we have to read that variance as the actual topology of reality. Project Liquid Midnight defines the vacuum of space as a high-viscosity superfluid substrate. This fluid behavior is governed by fractal geometry. Self-similar, scale-invariant structures dictate how pressure and form organize in nature, from the jagged edges of a coastline to the oscillations of a quantum field. Dimensions compress at their seams into a dynamic fractional manifold, stabilizing at 9.6 dimensions. The remaining 0.4 gap allows Hawking friction to vent. This venting creates a pressure gradient, giving empty space the structural tension to prevent entropic collapse. The mass-energy discrepancy currently attributed to dark matter represents the total pressure of this fluid exhaust venting through the 0.4 fractional seam. Accurate mapping of a fluid universe requires measuring along the geodesic grain of spacetime, following the path of least thermodynamic resistance, rather than the shortest Euclidean chord. We achieve this through the metric tensor, a Riemannian tool that weights spatial intervals according to the organic curvature and localized physical constraints of the vacuum. The total vacuum pressure is calculated through the dynamic liquid push equation. This formula tracks the physical thickness of the vacuum, its viscous drag, and the rotational torsion generated by spinning singularities. Gravity operates as the omni-push, the total thermodynamic pressure of the vacuum substrate squeezing inward. Mass functions as a singularity sink, creating a vortex that pulls the liquid vacuum inward, leaving behind hydrodynamic wakes as energy tunnels through the substrate. Standard models require fudge factors because they measure a straight chord through the void, failing to calculate the total fluid pressure acting upon these localized vortices. Theoretical cosmology reaches its limit at the point of verification. We can measure this topological pressure right now using commodity edge hardware. We developed the Bubble, a multimodal sensor fusion system that uses the gyroscopes, accelerometers, and magnetometers in standard devices to map localized physical anomalies. The Bubble operates on a philosophy of shared error. Every sensor has inherent physical limitations, noise floors, and drift. Instead of searching for an absolute truth in a single data stream, the Bubble aggregates raw, chaotic noise from thermal, RF, and inertial sensors to build a rolling probabilistic map. This data reveals a persistent plus or minus 0.01 jitter across all hardware. This variance represents the hardware-agnostic stochastic resonance of the vacuum itself, the local Hausdorff dimension of the manifold. By recording the raw jitter of commodity sensors instead of smoothing it over, the edge device natively functions as a low-frequency gravitational wave detector. The primary challenge in measuring any field is the observer. The sensor drifts, heats, and creates its own physical footprint as it moves through space. The Bubble addresses this by structuring raw data into a 24-variable lattice, divided into 4 primal cuts: the manifold, the sensor, the steganography, and the observer. A 25th variable, the level cut, acts as the system's independent auditor, monitoring the other 24. It strips away the observer's frame distortion, subtracting the hardware's inherent bias, isolating true environmental anomaly pressure from the device's internal noise. This establishes a rigorous mathematical boundary. It separates verified physical reality from apophenia, the ego-driven pattern hallucinations often produced by noisy sensors. The Bubble maps the environment without optical camera input. It views space as a 3D coordinate field defined by a probability-based boundary. Detection within this field is driven by the principle of asymmetric diffusion. An inhibitor wave quickly suppresses noise, while an activator wave slowly organizes the signal, generating a Turing pattern. Events like thermal spikes disrupt this diffusion, warping the geometry. The bubble flags anomalies when heat behaves against the norm, moving incorrectly or persisting. The system identifies anomalies through their divergence from a dynamic mathematical baseline, rather than relying on crossing arbitrary pre-programmed thresholds. Scaling this process across edge devices creates a localized probabilistic spatial field. Cross-referencing the 24-variable lattice across all nodes simultaneously, the system calculates a definitive probability of physical change within the environment. This method relies on discrete manifold mapping. Signals are captured as point cloud steganography, preserving high-frequency data that legacy systems smooth over. Using points instead of lines captures the raw topological flux, proving the vacuum is a dense, data-rich fluid substrate. The bubble framework provides a rigorous, pattern-based model of the quantum plenum. When we discard the rigid Euclidean grid and instead embrace the ambient noise of the universe around us, we stop reading the artifacts of our own tools and begin reading the structural truth of the liquid vacuum.